Hi there. So today we're going to go over some vowel classification and using two different approaches. One is a canonical comparison of coefficients of vowels, and the other is using a feed-forward neural network. So let's jump into our motivation. And this is all on the GitHub for vowel detection neural network. So let's hop into our motivation. So our goal is to use different approaches to try to identify a vowel, and this vowel is going to be given in the form of an MP3 file or like a WAV file, so something that is some type of audio spectrum. And from there, extrapolate or kind of process this data so that we can plug it into either some neural network or some kind of regression algorithm that will allow us to hopefully differentiate which vowel is being said. And this is kind of one of the first use cases of speech processing, is to determine what vowel is being said so that we could perhaps identify what number someone is saying in an automated please enter which number, 1, 2, 3, 4, or 5. So at a high level, we're working on the neural network classifier, and it has two steps. The first part is to generate what we call LPCs and train a neural network to identify what a vowel is based on its LPC. So on the left-hand side, we'll have an LPC value. On the right-hand side, we'll have the one-hot encoding or the associated ID of the vowel. The second way is to identify the vowel backness. So there's two types of vowels. There's front vowels like e, and a, versus the back vowels like o, and ah. These two don't really differentiate too much in American English, but they do in British English. And we do this in two different ways. But let's first review what are LPCs and how are they related to our task of vowel identification. So LPC stands for linear predictive coefficients, linear predictive coding, and we use LPCs to approximate a continuous waveform. So our speech signals of vowels are given as continuous waveforms. Our goal is to approximate them and kind of quantize them using a few coefficients. Originally, this was used to compress the number of data needed to reconstruct a waveform signal when sending a continuous speech signal across a telephone line back in 1989. As discovered by Bell Labs. But today, we also have figured out that LPCs have an inherent relationship to formants, or the fundamental frequencies that are created when your vocal tract constricts in a certain way to make a vowel. In other words, linear predictive coefficients are a way for us to quantize and figure out what a vowel is. All right. So some side notes is we've also downsampled our original sample from 44 kilohertz to 14 kilohertz, since the heuristic originally used at Bell Labs was 1 kilohertz per sampling rate. So, oh, sorry, 1 kilohertz per LPC coefficient, and since we're using LPC 14, we want to use a 14 kilohertz sampling rate. And additionally, we wanted to use LPCs because they're kind of this digital fingerprint or quantized fingerprint of what a vowel is. All right, so for this for this project, we've used both the MATLAB signal processing toolbox, but also found it a little bit easier for people who aren't in the linguistics community or in the science community who tend to use MATLAB, and converted this into Python as well, using librosa and SciPy and NumPy as well. And for the neural network training, we also use PyTorch. So let's go ahead and let's jump into our vowel neural network classifier. And again, anything on this left-hand side here that we're about to go into corresponds directly onto our actual Jupyter notebooks that we're running locally. So let's go ahead and we can either jump into the MATLAB script or this equivalent Python script. I'll go through the Python script since a lot more people are familiar with the Python script. And so what this is doing is it is taking the number of linear predictive coefficients and going ahead and processing them. So for our audio files, we are going to load them in using librosa. But we have this important step here, which is we really want to make sure that we only grab the middle of the files, since people could record them at different times. For example, they might wait 3 seconds and then say the first vowel E. Or for example, some people might have truncated the data, so they just say E right off the bat without waiting 3 seconds. We want to take the middle of the file as a kind of a heuristic so that we can make sure that whichever LPC coefficients or this kind of quantization of this continuous waveform that we're doing is always consistent across all the values. So that's this first part here, it's step number 2. Step number three is we're downsampling again for that 1 kilohertz per LPC coefficient. And the last part is we've also done a reintroduction of high frequencies by taking the difference of consecutive points. So, for example, if we have a point like this, so this is our waveform, looks something like this. We've actually taken the difference of each point. So, for example, here and here. So, for example, maybe this distance, maybe the derivative here is quite large. So, if we were to draw another spectrum over here, it'd be something like this. The first point would be very large here. Maybe here is a little bit smaller. So we have a smaller value right here. Okay, so our next point is here. And maybe it gets smaller and smaller and smaller. And maybe when we over the hump over here, we have a large value again. So now we have, a large value. And so now you can see how this seems to be much more choppy or increases the quote unquote frequency of our signal. Our intuition here is that in the inner ear or the cochlea, that because air kind of resists these high frequency sounds, we're actually having a heuristic here that increases the frequency of these or increases the prominence of these high frequency spikes here. And it turns out that when we are able to use this high frequency heuristic here, it actually does improve the identification of vowels. And this is more of a heuristic for how we're able to model the inner ear's interpretation of sounds when it's actually produced. All right. So from here, we return this downsampled audio file, and right now it is currently a NumPy array. However, in the MATLAB file, in the way that we did it, we just export it as a .mat file. Later, we'll come back to this on using the Cohen's d in order to try to figure out what are the vowels that actually differentiate using the effect sizes as seeing how much of an impact we would see in real life on these vowels. But let's go ahead and let's hop back into our vowel classification neural network. So here are the vowels that we're trying to classify. E, I, A, U, O, A. And what we're going to do here is we're going to load them in from our MATLAB file. So it's, again, an equivalent of this data over here. And we're going to go ahead and load them in as tensors. So we'll do this over here. That will be passed through our models. We're currently using a 3-layer model. So we have neurons here, which are our input neurons. And we have 14 of them, each for 1 to 14 of the LPC values. And on the output here, we have 10 neurons. And this is the 1-hot encoding for each of our 10 neurons. All right, so all of these, and we'll have another one here for 10 of these. Inside our middle right here, we also have a variable number of hidden layers. That's kind of what we're experimenting here. We're trying to see what are the number of neurons that optimizes the loss on the identification of which vowels they are. So it could be 1, it could be 5. Currently, for this example, we've just done 1 to 5, though there are some drawbacks on that, which we'll kind of get back to later. So let me go ahead and clean this up right now. All right, so for this model, we're just using a simple feed-forward neural network with a sigmoid, and we want to use a softmax at the end in order to kind of make sure that all of our probabilities end up at 1 at the end, which makes sense since we want 1 to be evenly distributed through those last 1-hot encodings, kind of similar to like some transformer models that use softmax at the end. All right, and for our optimization, we're using stochastic gradient descent, and we're also using a reduction of a sum. So we're taking the mean squared error loss, and we're adding them all together for this example. So for our model training here, we're going to take the vowel predictions, all 128 of our vowel predictions, and we're going to aggregate the sum using mean squared error, and then we're going to use our stochastic gradient descent here to backpropagate. And for this, we essentially do this over and over again. In fact, we do this, this is some extra helper functions for plotting the data. We actually do this for how many iterations? We do 10 trials per each hidden layer size. So if we have 1 hidden neuron, we're going to run that trial 10 times with randomized and randomly seeded weights and biases. Same thing for 2 hidden neurons, 3 hidden neurons, 4, and 5 hidden neurons. Again, that's still 3 layers, the first one being 14, the second being some variable hidden layer size, and the last one being 10. We do that 10 times. So essentially, we're running about 50 of these tests. And at the end, we go ahead and aggregate all of these values into a 3D NP array. And so what that looks like is we'll have, for example, this array right here, which will be all of the hidden neurons with all the hidden neurons with one layer, and over here, we'll have our 10 trials of having only one hidden neuron. And each of these will be an iteration. So this is the first trial, second trial, third trial, etc. And in each of these squares, what we'll be doing is we'll be placing in the loss at recorded at some predefined clock rate. So we decided to record the values every 10,000. Let's see, I believe it's right here. We decided to put our clock rate at 1,000. So after every iteration, after every 1,000 iterations, we'll go ahead and we'll record a loss right here in one of these boxes. All right, let's clean that up over here. All right, so essentially we let this run many times. And as we aggregate our data, here are our results. So what it looks like is that after doing 10,000 training iterations, it seems that we have the best values or the best loss at using 5 hidden neurons. And something that we wanted to kind of highlight here, and is one of the limitations that we put in this README, is that when we have only 1 to 3 neurons, so this whole section right here, we're only allowed 2 to the third possibilities, and 2 to the third is just 8. So if we only have 8 possibilities and 10 one-hot encodings, it kind of makes sense that there would be some error and some loss in that. So it makes sense why number 4 and number 5 are doing the best. Something also to note, though, is that there are some times where 4 actually outperforms 5. For example, we have 4 over here and 5 over here. It seems that this one was better than this one here. And I think more testing is needed with more hidden layers and also different neural network architectures. So when we see this, it seems that we have a better and better loss for increasing the number of hidden neurons. And that makes sense because we'd likely be convexifying this formant or LPC to vowel classification task. Over here, we've plotted the median loss at the very end. So the median loss is the very end loss. And it seems that over here, it seems that we're actually doing a lot better. However, it does seem that we are kind of getting some diminishing return for the number of epochs, oh, sorry, for the number of hidden layers as we increase, or the hidden neurons in each layer as we increase. Lastly, over here, these are heat maps of the classification. So this is a heat map classification of one of the hidden neurons, with a neural network with one hidden neuron. And that seems to make sense here that it does well and performs well on one of them because there's only one hidden neuron. So it's really only able to learn 1 to 2 of these convexified relationships. However, if we look at 5 hidden neurons, it seems to do a lot better. For example, the yellow means how close it was to actually being correct. So for example, 1.0 here means that is correct. That's the difference between, or that's the loss. So this was 100% correct, almost 100% correct. And you can see that for most of these 5 neurons, they are mostly staying in their correct values of having yellow here. And so from here, we're able to conclude that the best way to do these LPC coefficients is to use more hidden neurons and to help convexify the issue. Last thing was a quick tangent. Before the people at Bell Labs worked on actual vowel identification, they wanted to know, is this vowel a front vowel or a back vowel? And so we have this table at the front of which vowels are front and which ones are back. For example, a, those are all front, back are u, o, a. And so what we've done here is we've calculated the effect size, or how likely we are to see the difference between the front and the back vowel coefficients, LPC coefficients, for 218 samples. And so from this, we were able to see that formant 1, or LPC1, and LPC2 seem to be extremely prominent, in addition to also LPC8, and there should be one more as well, LPC10. Something that's surprising here is we know that formant 1 and 2 are related to height and backness. However, these two over here are not as expected, and so perhaps this could be due to our small sample size. Again, all of these findings are documented into these more full write-ups over here and the things that we just went over. And for the most part, these are kind of just a first type of intuition on trying to see what were the people at Bell Labs thinking when they were working on their first classification tasks. Next time, we'll be working on MFCCs, the same type of coefficients or parameterization of waveform speech that are used in modern systems like Whisper that from OpenAI. Thank you so much for listening, and hopefully you'll see our next results soon.